That's my new thing. Just go with it. So the book, okay, so let's see. Go into the book. Okay, it's Pearson eText, which I'd like to get a PDF of this one, but I don't know how to do it right offhand.
I would like a PDF of it too, where I can go back and view it outside of this course.
Yeah.
Because if I don't understand it and it's a subscription-based thing, I don't want to have to go ahead and pay another subscription.
Yeah.
You know.
Well, I will tell you this. Let's see. Yeah, we'll do this. Wow. Okay. Okay, so here's what. Okay, let me get this. Well, you can't zoom it down. Okay. Okay, so let me click this to get rid of the titles. So we're going to skip this one. We're going to go to this one. And I'm going to basically kind of set up. Let me see what he's got first. Okay, and he may not immediately go to a pipe problem, but if he doesn't, that's what we're going to go to. So first thing he does is he comes up, this is a good thing, he comes up with the symbols, the quantity, and an MLT representation and an FLT representation. And he goes through it, and we may make use of this for a minute. Okay, so that is a great question. Let me answer that. And I'll pick off some of these and I'll show you what that means. But let me go down and see if he starts with a pump. I mean, with a pipe. He starts with a pump. Interesting. Okay, so let me grab this. So first, let's grab. What I'll do is I'll go over here. I'll get a new page, and instead of grabbing them image-wise, I'm just going to write them down. So the terms I'm going to write down, I'm kind of focused on are P for pressure. So I'm going to work on pressure, length or dimension, or diameter. Let's say diameter. Viscosity, density, velocity. And so this thing has units of PSI, right? Or you could say pounds per inches squared. Or you could say it is a force over a length squared. So if you think about it, here, let me do this. Let me grab this, grab this thing and move it down a little bit. If you think about it, we've got a couple of things. We've got F is equal to a force. L is equal to a length. T, a capital T, is equal to time. And then we've got, I should have moved that, M is equal to mass. So he's breaking it to FLT or MLT. Now I'll tell you why that or exists in a second. So in this, okay, this is going to sound really weird. Okay, pressure is listed as an F over L, right? Or what he likes to do, and most everybody, FL to the minus 2. Okay, so that's what a pressure is represented as. Force over an area. Makes sense, right? But, and this relates back to chapter 1, but in fact, F is equal to MA tells you that a force is equal to a mass. Acceleration is so many feet per second squared. So now I can say M is equal to F, L minus, that's an M, L to the minus 1, T squared. I just move the L over to the other side, whoops, and move the T over to the other side by dividing. So I got these two, so F is equal to MA gets you that. So I got these two conversions here. So you can think of these now as special conversions. Oops. These are special conversions that I can convert. Now, does it make sense? Well, that's the kicker here. It doesn't, because let's say if I took in this and I say I wanted to convert it. Okay, so technically, this is the FLT representation of pressure. Makes sense, right? So now I put in the F, so I just take this F and put it in here and then write that out. I get M L T to the minus 2 times L to the minus 2. So that L to the minus 2 is that one. This, in fact, is just the F. But you look at it for a minute and you're like, what the heck is this? Okay, there's your units of pressure. Okay, so let's say I take my two L's and I'll get L to the minus 1, T to the minus 2. So a unit of pressure could be thought of as a kilogram meter second squared. And you're like, what? Makes no sense. But that is the representation. Or it could be, you know, a slug, unit of mass, a foot second squared. But if you look back at his book, you'll find, okay, find pressure. You see pressure? Okay, here's pressure. When you look at that right there, that's it right there. M, L to the minus 1. Okay, M, L. Here, I can just do this. I think I can do this. I'll do this rectangular grab there. So there's your pressure right there. Two representations of pressure. One makes perfect sense. One is a little bizarre. So there is your one representation. Doesn't make a whole lot of sense. But then you got this one, which makes perfect sense. So it is the representation of it. Now, are there times you would need that? Yeah, actually there is. Fluids is a good example of that. So if you go straight into this, okay, so let me tell you where this came from. Back in the, okay, I'm not sure I have my years right, but all the way back to the 1900s and even into the 1800s maybe, this started in about 1920 or something, it solidified. So what they had done is they took all these different pipes. And so then they basically said, well, I'll look at the pressure up here because they could figure out pressures, you know. So you pressure 1 and pressure 2. And they knew Bernoulli's back then, but they were like, okay, there's some losses taking place in here. How do we classify these losses? Okay, so then they're like, how does the pressure change as a function of what? And so then they would shove different fluids in it, and it would be different. They would take the length of it, and what they immediately figured out is they were like, okay, well, this thing, they were actually doing this. They noticed this. They noticed if you had 4 foot of pipe and 8 foot of pipe, the pressure would be linearly varying as they went through there. So they were like, okay, we have that. Then they were like, well, we shoved the thing faster through it, and then we changed the diameter. And then they looked at it and they were like, okay, wait a minute. We got one variable here. We got 2, 3, 4, and then 5 variables. They were like, okay, how do we quantify it? So they collected literally reams and bucket loads of data. And this guy came along named Buckingham Pye, or see if I can find a reference in the book. Let's see. Let's see if we can find, we're just going to go through, see if I can find a reference. Definitely not there. Okay, dimensionless numbers. Euler, Reynolds, Freud, River, Mach. Okay, not there. Buckingham Pye, okay. It sounds weird, but if you read the Buckingham Pye theorem, okay, he's basically made it really long here, But effectively, let me just show you what it is. It's better just to show you this now. This theorem kind of came out of observation, and it mostly, to a large degree, it came out of this pipe experiment. What they noticed is, now what I'm going to do is I'm going to list all the variables. So he has P over L, and then I'll put an arrow there, mu, and then density, and then velocity. This one I can do, and diameter. So the diameter is a length. This is a length feet per second. So that's pretty simple. This is a mass per unit volume. This is pressure, okay? So before we had a force over a length squared, but now we have it over, because we have it over another L, so we have that. So this one I've got to go back and look at. I should know that right off the top of my head, but I'm not going to worry about it. Let's see. I'm not. This one? That one's density.
What's the one above it?
This is viscosity. Okay, so, you know, if you put a more viscous fluid in it, it changes and you run it at, so what they were doing is they would put a different fluid in, run it exactly the same speed, exactly the same diameter, and they notice a different pressure. You know, yeah, and so they're like, what the heck? And so they collected all this data. Well, Buckingham Pi states that, okay, let me find the units to this first. Actually, I should be able to do that right off, because shear stress is equal to mu times the change of velocity. Well, I better make sure I'm doing it right. I don't want to mess up. So what I'm gonna do, I'm gonna go back to this table, which was the first. The first one, and there's the table. And so you look at the, hang on. Oh, where did it go? So you look at this one right here. So here's your dynamic viscosity. So you know what I'm going to do? I'll leave this up and I'll bounce back and forth to it. So I'm going to take this in FTL to the minus 2. FTL to the minus 2. So then what I'm going to do is I'm going to say, okay, you've got to choose one or the other. You never find a variable. So what you notice is F and M are interchangeable. You'll never find a variable that has right. So, you know, pounds per square inches. And you'll never find anything like that with a pound and a slug together. They always remove one of them. So what I'll do is I'll say, since I have an F here and an F here, I'm going to go ahead and convert this to the FLT representation of density. Let me find it first. F T squared L minus 4. F T squared L minus 4. Then what they discovered, this was kind of out of, I don't know what happened back then. I don't know if somebody said, hey, let's try this. I don't know how this happened. But they were like, they noticed some behaviors that were kind of strange. And then they came up with these non-dimensional variables. Now, if you think about it, we do this all the time. Like in finance, it's rate of return. So if I invest $100 and you invest 1,000, we make 10%. We both made something different, but if you divide by what you made by what you invested, we both made the same. Yeah. So it's basically the number of dollars over number of dollars. And it had there's no units. So usually in finance, they'll say percent. But the only thing percent does is take 0.1 and turn it to 10%. So, the answer is 0.1. But in finance, they want to know a percent. So, but let's say you don't. Let's say I want to know a non-dimensional number. How many of them are there? Well, it turns out if you list, you have one variable, two variables, three variables, four variables, and then five variables. So there's five variables sitting there. And then they're like, how many dimensions do I have? What's meant by dimensions? Well, I either have an FLT or I have an MLT. I have nothing. All that sits in here is F, L, and T. Now, if I had an experiment that had temperature, I would have another variable, and then it would be MLT theta or something like that. But I don't. I have three. So I have an FLT or an MLT. So I have three. So it turns out Buckingham Pi says 5 of those minus 3 gives me there are 2 pi terms here. Now, okay, these pi terms meant nothing until they did a plot. When they did a plot, they were like, holy crap. I don't know that they said holy crap, but everything fit on that plot. So then they were like, this is very important. So the theorem came, you can make all sorts of theorems. There are billions of theorems. Probably, 900 million of them are useless. But this one turned out to be very valuable. So how do you go about it? So what you do is you go in and say, well, I'm going to have 2 pi terms. Let's say one pi term is going to have a rho, a mu, a velocity, and a diameter, say. And so you're looking at it and you're like, well, if I multiply those all together, I'm not going to get a non-dimensional number like a rate of return or anything. So I want that to be non-dimensional. So the pi's are all non-dimensional, have no dimensions. So then the key is, how do I do that? Well, what you do is you say, I don't know, let's say, I'm going to say R, S, and T. Well, now see, there's a little trick here. There are 3 of these. So you can only have 3 of those. You'll find out if you put another one right here, if you have 4 equations and 3 unknowns, and I'll develop the equations in a second. But if I did, let's just say RSTL. Let's say we put one. So now I want this to be, if eventually, something that has no dimensions. So how do I do that? Well, I'll take each of these terms. I'm going to take this F T squared L to the minus 4. I'm going to take this one. This is the density one. And then I'm going to put it in parentheses. I'm going to put an L up there. And then I'm going to take the viscosity one, which is this one, which is F T L minus 2. And I'm going to put an R up here. And then I'm going to take the velocity one, which I don't even have to look, but that's that. Length T to the minus 1. And this whole exercise would be useless except the fact that it actually yielded something. And diameter is just a length. And it has to, all this has to be such that it's F L T to the 0, 0, 0. It has no dimension. So how do we get that? We grab the F and we say, let's look at the components. Well, on this first one, I have L. Okay, so I have F to the L. And then I'm going to add that. So in the components, you add the exponents. So in other words, like if I had 2 squared and 2 to the 5th power. That's the same thing as 2 to the 7th power. I just add this and that. So I'm just adding these exponents up there. L, this one has R. That one doesn't have nothing. L, there's no more F's. So that has to equal 0. That 0 came to right there. And then I grab the L. Okay, so now I got minus 4L. The next one I have minus 2R. And then the next one, okay, I'm still on L, so I see that is an S. That's not a 5, that's an S. Plus S. And then plus T. All that's got to be equal 0. And now I got the time thing. So I got 2L, so right here, 2L. And I got R going right there, plus R. And they got minus S, minus S, and that's equal to 0. The problem is they got too many unknowns. And so what you can do is just guess one. I'll just say I'm going to set L equal to 1. If I set L equal 1, then my equations become, okay, my F equation becomes 1 plus R, or, sounds weird, R is, R is equal to minus 1. So go into the L equation, and it's, okay, so I'm just saying L is equal to 1. Just saying, I got too many. I got 1, 2, 3, 4 of these, but I only have 3 equations. So I say minus 4 minus 2R plus S plus T equals 0. And that last time equation gives me 2, because I get 2L plus R minus S equals 0. So if I stick the R in here and move the S over, I'll get S is equal to 2 minus 1, or S will be 1. So I get S equal 1, R equal minus 1. So now I got to look real closely, and this one's the one that sometimes I've messed up before. It seems that's funny that the simpler the thing is, the more you can mess up. So I got R and I got S. So I'm going to write the equation out first. 4 minus 2 times R. R is minus 1 plus S, which is another 1, plus T. Okay. Okay, this and this go together. So first I got minus 4 plus 2 plus 1 plus T equals 0. Yeah, negative 1. Move it to the other side, and you get T equal 1. Okay, so those are your things. You got these 4 things. So now if you write this pi term down here, I think, okay, let me just, instead of rewriting it, I'm going to copy it. So my copy was, this is my pi term. Okay. Do a copy, because I don't want to copy and put a mistake back in there. Okay, so I know it has to be no dimensions, but here's what it actually is. Rho to the first times mu, what was R? To the minus 1. Velocity, wait a minute, which one is it? S. Oh, S is 1. V to the 1, or well, I can put the, and then D, T, yeah, that's it. So that's 1. So in fact, pi 1 is equal rho velocity diameter over mu. Now, they discovered this using this method. And if you go back to the textbook, you go, I don't know if it's this, what we get to the end. Okay, I push the button. Buckingham pi. Oh. Okay. Okay, see, I think what happened there? Important. Oh, okay, that's where I wanted to be. Okay, so I don't know what happened there. So important dimensionless numbers. And the first one, no, the second one. If you look, that's exactly what that is. So they discovered this. So if you do a snippet, do a new, and grab it, and go back to our thing, and just drop it in there. Oh my gosh. Okay. Yeah, here. It turns out that was the Reynolds number. So the length is just a length. Okay, so for pipe flow, it turns out that your length is your diameter. For an airplane, you know, you're going to have a Reynolds number there. They use so this L is like a length, a characteristic length is what they call it. Characteristic means if you change it in a particular way, it's going to have an effect on this. And so what they did for aerodynamics is they do the chord length. For pipe flow, they do a diameter. The chord length is the length from the tip of the wing to the tail of the wing. And so if you got a wing that sits there, that's called the chord length, the length from here to there. So if you double your size of your wing, it'll double that chord length. Now they decided they didn't want to use this length, so you never see that length used. You always see the if you look down on the top of the wing. I think the reason being that happened, yeah, it did better because if you look at it, that's the whole area that the pressure is put on to lift the wing up. So it had more characteristic. It was more characteristic of it. So it turns out all these non-dimensional numbers can be extracted out of a group of experiments that you do thousands and thousands of them, and you find out, okay, I can do a plot. And the plot is such that it was interesting because you have two pi terms here. And the two pi terms are such now I can take all pipes and put pi 1 and pi 2 and plot everything. And so it turns out, they're going to look kind of like that. But in reality, there was one other pi term. Okay, so when they were constructing these experiments, they were using the same type of material throughout. It turns out if you use make a pipe out of concrete and you make another pipe out of glass, the smooth glass doesn't have it has another effect to it. So there was another effect, and what that effect was, when they figured out the pi terms, they created this diagram. And then they were like, oh, there's another term. They did more experiments. If you have a rough pipe, you zoom in on the pipe, and what you do is you measure the relative roughness of the pipe over the diameter. So they just came up with, hey, this is another non-dimensional term, like a pi 3. And so it turns out you end up with pi 1 is equal to some function, I didn't put the F in there, some function of pi 2, pi 3. And that's what you need for pipes. Well, it turns out, and let's see if I can find out where we put that, where he did this in this thing. It turns out, table of contents, we go in here to chapter 9. It's got to be in here, but I'm not sure it is in here. It might be in the next one. There he talks about the Reynolds number, which we already did. Well, what I'm looking for is something called the Moody diagram, and that may be in here. And he may not be listing it in this point. You know what? I don't think he is. Okay. Pipe fittings and transition. Okay. Okay. It might be right in here. Yeah. Let's see if I can find it in here. So he goes through, okay, this is great, laminar flow. Okay, so we're starting, and then he's going to go into turbulent flow. And what he's going to say is, hey, wait a minute. It is a function. Now, this part that got sucked out is part of the non-dimensional thing that he's going to deal with. But Reynolds number you can see in there, and E over D, and length over diameter. And then you get down here, and okay, so he comes up with this equation, which is called the Darcy-Weisbach equation. This is what's used in pipe flow to determine the loss of energy from one location to the next. But the question is, what's F? If you do down through, you'll see the Moody diagram, and this is it. So what you see And this is something, let's see if I can maybe get it out of here. Wait a minute, let's see. Maybe is it F11? No, that's that. Let's see, F11. Okay. Oh, it went and made itself. Okay, now how do I, let's see. I'm going to try this. Is it that? Or is it, I'm trying to snip the screen. I forgot how you do that. But you know what? Maybe I can do it. Oh, I can do it there. Okay, so I'll snip the screen. I'll get the whole thing. So let me get back over to here. And so the end result is this. Oh, that's funny. So if you look at it, and I like the way he highlights this. There's one of your non-dimensional terms. There's the other non-dimensional term. And there's a third one. So those are your 3 pi equations, or 3 pi terms. Now, how do you go about doing this? Let me just see if I can do a simple problem. Let's say we have water. Exactly, that's the key. So what we're going to have is f is equal to a function of the Reynolds number and the E over D. That is exactly what this is. This equation is, this chart is an equation. So let's see if we can figure out how to make it work with a problem here. So let's say we had a piece of pipe that was, say, 1 foot long, or let's make it more interesting. 100 foot long. Let's say its diameter is 0.1 feet. Or do I want to do, I'll do the diameter. And then I'll say the velocity flying through there is, say, I don't know, 20 feet. That's not a 2. 25 feet per second. And we're going to say we're sending water through it. And the reason we're sending water is because I know the numbers for water. The density for water is 1.94 slugs per cubic foot. And I know the viscosity is 2.34 e to the minus 5. And let's see, pounds, seconds, foot squared, I think. We'll look at that in a minute. So how do I know that? You can just basically go, it should be in this book. Problem is I don't know exactly where to look in the book. And so you can go in and find, this is okay, so he's given me that. Yeah, let's see. How about we do viscosity of water? Okay, wait a minute. In down. Okay. Let's see what happens if I do that. That's okay. We don't want that.
What's the inch pound per foot cube?
Inch pound per foot cube. That's a good question. I'm not sure. Let's try that. Okay, so he's got temperature, but he's got a really high temperatures there. Those are really high temperatures. Okay, so that's really high temperatures. Okay. So what I've always used is 2.34 e to the minus 5. And that's kind of an accepted thing. 2.34, and then they got this e to the minus 5 up here. So obviously you can tell you start heating it up, the water up. I mean, things start changing, and they change moderately fast. So if you got hot water or warm water, or even up here, it basically changes quite a bit. But we're just going to go with that. Let's say we did water at about 60 degrees. So you're running in at about water at 60 degrees. The question is, what's the delta P? I don't know. So what you do is you write Bernoulli's equation. Okay, this is going to be listed at 1. That's going to be listed at 2. We're going to say we're on ground. Gravity is this way. So P1 over gamma plus Z1 plus V1 squared over 2G. Now, this is the key. The Darcy-Weisbach equation looks like this. And then P2 over gamma plus Z2 plus V2 squared over 2G. Now, if the pipe didn't change diameters and you didn't include losses, ironically, the two pressures would be the same, which is not even possible. So in order to calculate the pressure loss, you have to include results or information from this Moody diagram. This Moody diagram has some beautiful curves on it, but in fact, there was a bunch of data points that they fit over and over and over, and that's the reason, this is a curve that has been fitted with lots of data. And there's a region right here which is called credit. So what happens is it behaves when it's flowing really slow, it basically traces out this curve. And then somewhere around in here, it's a very gray area. He calls it a critical zone. Thing is this is an unstable zone, meaning it can pop into full turbulence or a transition. You could run one experiment and it might look like this. You could run another experiment and it might look like this. There are.
So is that like where you would have possible cavitation or whatever?
No, it's basically where the flow is kind of swirling, but like if you think about it, you're driving along and the flow is swirling over your car. But as you go faster, the swirls become smaller. And so, as you go faster, things become more predictable. But as you're going slower, you can just put your hand out and effectively change the flow pattern a lot over your car. So it becomes it's like a chaotic region in which there's larger swirls and things happen. What happens here is the swirls over in this region become much smaller and therefore more predictable. And so you got this transition region, which is moderately predictable. This critical zone is like completely unpredictable. It's like weather behaves that same way. You turn on the weather and you predict something and it's completely different. I mean, there's a huge nonlinearity in fluids, and that's what's creating this. But if you're going slow enough, your laminar flow, you realize it's only a function of the Reynolds number, and it looks like that. Really simple. But if you get over in here, it's basically much more difficult relationship. So how do you find this? Well, first of all, the elevation will be the same, or we'll make it so the elevations are the same. Those are gone. The velocities, believe it or not, are equal. The pipe diameter didn't change. Those cancel. And so then you can take the pressure and move this pressure to this side and this over here. So you can say, you can say it this way. P1 minus P2 over gamma is equal to, and moving that over, the F L over D, V squared over 2G. So let's say we wanted to know what the delta P is. Let's go ahead and call that delta P, because that's what this is. This is 62.4. This is F. The length of our pipe was 100, wasn't it? Yeah, we made it 100 feet long. Oops, that's the wrong place. What? 100. We made it 100 feet long. The diameter we made 0.1, didn't we? Yeah, 0.1 feet. The velocity was 25 squared over 2 times 32.2. So at first glance, you see there's two terms in here. So if you wanted to, delta P is equal to, okay, so I'm going to go ahead, 100 times 62.4 times 25 squared times 2 times 0.1 times 32.2, and this is all times F. So I'm going to take the F off for a second and then use this picture thing to find that number. Let's see if I can find, okay, did I have it up? Yes, I did. That's from the last class. Okay, see if it figures it out. Did it copy it down correctly? I think it did. So, okay, give me a second. 605, 590.06211. And then I got my F, because I got my F here. So delta P is equal to that. Now, what we need to do, we need to figure out how rough is the pipe. So we'll just say our pipe was pretty rough. 0.0, we could say 0.01. Yeah, let's just say 0.01. It's a pretty rough pipe. So we're going to stick to that line. We're going to stick to that one. Then we're going to say, what is my Reynolds number? Well, my Reynolds number is just, Reynolds number is equal to rho, velocity, diameter, over mu, which it's written this way, but that's the same thing that is what that is. So I get 1.94 times the velocity of 25 times the diameter of 0.1 over 2.34. This will be interesting. E to the minus 5. I want to see if it can figure that one out. That will be really interesting. Oh, couldn't recognize it. Let's see if I can get it further out to the page here. Okay, let's try it again. No, couldn't recognize it. So, how do you go about doing this so it can recognize 2.34. Oh, I know, times 10 to the minus 5. I bet that's what it is. Okay, you did it that time. So the Reynolds number is, let's see, 207, comma, 264, and the digits really don't matter. So 200,000. So here's a million. This is 100,000. So here's where I'm at, 200,000. So I just keep going up, 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 up. Keep going up, 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 all the way to where I take this line and I follow it out, and pow, there's where they cross. So now what I'm supposed to do is I'm supposed to do this. I'm supposed to find a ruler, make it at 0, and wherever they cross, I draw a line straight across. And you got to be careful because this thing is seems like it's logarithmic sometimes. Let's see, 2, 4, 6, 8, 10. So that would be 0.038 would be that number, 0.038, 0.038. So I get a friction factor from that diagram F is equal to 0.038. So then I just multiply that. Okay, so let me try that. I'm going to try this. Okay, so here's what I'll do. I'll do this. I'll do a copy, and I'll just paste it right there. And then I'll do this. Let's see if it will allow me to do this. 0.038. And let's see. All right. Okay, come on back. Oh, it did. 2, 3, 0, 1, 2. This will end up being pounds per foot squared. Foot squared over inches squared. Now, I should be able to do this. You think? You know what? I'm going to make him do that too. There's some extra digits up there. Let's try it. Let's see what happens. Oh, it's doing some extra funny stuff. Equals 159 or about 160 psi. So that's what it would take to get that to go through there. You'd have to have 160 psi to get that to go through that pipe. So the sequence is pretty simple in a way. You're going to find your Reynolds number, and you're going to know what your pipe looks like, and you're going to find where they cross and come straight across and pluck out the friction factor. And then, of course, you're going to use it in the Bernoulli's equation. And that's pretty much it. Being able to read this diagram is all over the FE exam, or whatever that exam is called. I forget what that thing is called now. It's called something. So that's pretty important. So I think what we'll try to do now is, let's say, I'll assign some problems on the fluid momentum, and then I'm going to go straight into this chapter, and that's going to be the next assignment. Okay, so let's see. What does his problems look like? Okay, that's that. Okay, so this is great. Where are the problems? Oh, okay, so he's got like 5 examples. Let's see what they look like. Okay, I click there. Okay, so he starts off by saying the 6-inch galvanized iron pipe transports water at a temperature of 100 degrees. Determine the head loss and pressure drop in a 200-foot pipe that flows. Oh, is it? Oh.
Sorry.
Oh, no, that's okay. I don't want to go too long. So maybe what we'll do is we'll come back and pick up right here. So but between now and then, I'll send you an email. So, yeah, let's stop this thing.